Underwater acoustic sensors. Underwater acoustics is the study of propagation of sound underwater and the interaction of mechanical waves that constitute sound with the water and its boundaries. It has many applications ranging from oil industry to aquaculture and study of marine life. Maximum underwater deployments rely on acoustics for enabling communication combined with special sensors that have the capacity to take on unstable environmental conditions of the oceans. UASNs consist of a number of sensors and vehicles that can self-organize in an autonomous network which can adapt to the characteristics of the ocean environment. What is underwater acoustic communication? Underwater acoustic communication is a technique of sending and receiving messages below water. Why do we need to communicate underwater? Ocean bottom sensor nodes can be used to collect oceanographic data, to monitor pollution, and to explore offshore. Also, UUVs and AUVs equipped with sensors will find application in exploration of natural undersea resources and gathering of scientific data in collaborative monitoring missions. Working principle of acoustic sensors. An acoustic wave sensor is an electronic device that can measure sound levels. When an acoustic wave travels through a certain material, it is influenced by the different material properties and obstacles it travels through. Any changes to the characteristics of this traveling path will affect velocity and amplitude of the wave. These characteristics are translated into digital signal using transducers and can be monitored by measuring the frequency characteristics of the sensor. Practically all acoustic wave devices and sensors use piezoelectric materials to generate the acoustic wave. The sensors normally use two interdigital transducers, IDTs, that can convert the incoming signal into a mechanical wave signal through a piezoelectric substrate. What they do is turning an electrical signal into a mechanical wave and converting it into an electric signal again. Methodologies. Modem physical layer. The physical layer defines the mechanism for transmitting bits over a physical link channel connecting network nodes. The transmitter converts bit streams into a physical signal that is propagated through the physical layer. The main issues tackled by the physical layer in an UASN and discussed throughout this section are as follows: interface to physical transmission media, modulation, efficient carrier sense, collision detection, bit rate, and many others. Medium access control layer, also called MAC protocols, manage access to the communication medium. Without proper management of the transmission medium, collisions of unrequested communications may degrade overall network performance. Hence, the basic objective of MAC protocols is to avoid collisions and to deal with factors like energy efficiency, scalability, and latency. A collision occurs when two or more data frames arrive at the intended receiver simultaneously, and MAC protocols try to handle this time uncertainty by slotting time or sensing the channel prior to transmission. A problem that comes along with the long propagation delays is spatial unfairness because the packet reception time depends on the distance to the transmitter. The channel becomes free first at the transmitter and later on at the receiver. Hence, Nodes closer to the transmitter are able to gain access to the channel before nodes closer to the receiver. Reservation access. This technique consists of reserving the channel prior to transmission of the actual data packet. In order to do so, usually short control packets are sent before transmission. By reserving the channel, the frequency of the collisions of data packets is minimized and the additional traffic introduced by the control packets is compensated for. Handshake access. In this approach, whenever a transmitter wants to send a data packet, it first sends a control packet informing the other nodes that it has data to send. Upon reception of this control packet by the intended receiver, it replies if the channel is not being used. After receiving this reply packet, the transmitter can start the transmission of the data packet. However, this reservation mechanism cannot guarantee collision freeness because of the well-known hidden and exposed node problems. A solution to the handshake access is the propagation delay tolerant collision avoidance protocol. This protocol splits the transmission of the CTS packet so that it arrives at the transmitter after twice the maximum propagation delay. While waiting for the CTS packet, the transmitter and its neighbors can perform different actions such as transmitting data packets or starting the handshaking process for another transmission. Routing layer. Routing is considered to be one of the most important aspects in any multi-hop network. The routing layer is in charge of selecting the most convenient paths to successfully deliver the data to the destination. In some underwater network applications, there is a requirement for short network deployment times. Moreover, these applications do not allow previous deployment planning. In such cases, routing protocols determine the best routes to the destination without any pre-existing network knowledge. Some parameters like mobility and energy efficiency also help in better transmission of data. Mobility. There are many underwater network applications where mobility is required at least in certain nodes. In depth-based routing for underwater sensor networks, each sensor calculates the forwarding action taking into account the depth of two consecutive nodes, its own depth and the depth of the previous node. When a node has data to send, it broadcasts the message. Depth calculation and comparison are executed by neighbor nodes. In this line, nodes with shallower depths than the sender accept messages while dropping the other ones. The main disadvantage of DBR is that all nodes need a depth sensor, increasing the consumption and cost. Energy efficiency. Routing protocols that focus on energy efficiency are presented. Energy is a fundamental aspect in the type of network deployed. One widespread technique in radio frequency sensor networks which can be applied underwater is clustering. Deficiency in current communication. Future ocean environment will be increasingly complicated. Radio waves propagate underwater at extremely low frequencies and require large antenna and high transmission power. Optical waves do not suffer much attenuation but are affected by scattering. Acoustic waves are the single best solution for communicating underwater. Conclusion. While research on underwater sensor networks has significantly advanced in the recent years, it is clear that a number of challenges still remain to be solved. With a flurry of new approaches to communication, medium access, networking and applications, the field of UASNs must develop fundamental insights as well as understand what stands up in practice. We are encouraged by the broadening of the field to consider different options spanning from high performance with high cost and to low cost with lower performance, and including mobile, human-supported or autonomous, deployable and stationary configurations. For these reasons, we believe that the greater use of test beds and field experiments is essential, as it will support accurate performance analysis and system characterization. Integration and testing of current ideas will stress the seams that are often hidden in most focused laboratory research, such as total time cost, energy requirements, and overall robustness in different conditions. These are the references. Thank you.